GCSE Physics boosters, the national grid. This is carrying on from the last video about transformers and basically a bit more about what they are used for. Now, if a transformer is 100% efficient, then the power we put in must be equal to the power we get out from conservation of energy. Now, transformers are actually very, very efficient. They're about 98% efficient because they don't have any moving parts, so there's no friction. They do lose a little bit of energy, but we are always going to assume that they are 100% efficient. Now, one of the equations for power, which you're supposed to learn, is P equals VI. Power is voltage times current. So look at the diagram. Voltage times current in has to equal voltage times current out. So if the voltage gets bigger, what's going to happen to the current? Or if the voltage gets smaller, what's going to happen to the current? Well, in a step-up transformer, the voltage gets bigger, so the current has to get smaller. If the voltage gets 10 times bigger, then the current has to be 10 times smaller. Why? Because the power has to stay the same. V times I has to stay the same. In a step-down transformer, the voltage gets smaller, the current gets bigger. Okay, that's the opposite. Why? Because V times I, has to stay the same. So, if a transformer is 100% efficient, and we will always assume that they are, then power in equals power out. And here's a smelly equation which is on the formula sheet. I wouldn't worry too much about it. Basically, remember, if the voltage gets 20 times bigger, then the current will be 20 times smaller. Okay? However many times the voltage gets bigger or smaller, then the current will get smaller or bigger. Okay, it's the opposite. Let's have a go at an example. So here's a transformer. Now, a transformer steps down 230 volts AC to 12 volts AC to supply a CD player with 60 watts of power. What current does the CD player draw from the transformer, and what current does the transformer draw from the mains power supply? So have a go at it, pen, paper, calculator. I'll show you the answer in 3, 2, 1. There you go. So first of all, the CD player is 12 volts and 60 watts. So another equation, well, it's the same equation. I equals P over V. Yes, so 60 over 12 is 5 amps. So the CD player is getting 5 amps. So what current is coming from the mains power supply? Well, look at the ratio of the voltages. It's a step down transformer, so the current must be 230 divided by 12, whatever that is, that's the ratio, and it will be that many times smaller. So the current going into the transformer will be 0.26 amps. Okay, so notice that in this case, the current is getting bigger, the voltage is getting smaller. So what's that got to do with the national grid? Well, first of all, consider this. We've got a 12 volt power supply, 12 volts AC, and we've got a 12 volt bulb, and the bulb is very happy. It's getting 12 volts and it's nice and bright, a nice bright bulb. Now look at this. What we've done is we've connected the power supply to these cables, and these cables represent power lines. Okay, if you like, the power supply is a power station, and then we've got all of these power lines, and so miles and miles away is the bulb, which could be a house or a factory, and in this case the bulb is dim. Now, why is it dim? It is dim because we are losing energy. We are losing energy in the cables. if you actually touch the cables, and don't do it if your teacher's demonstrating this because you might hurt yourself, but if you touch the cables, they would actually feel warm because they're giving off heat energy. The bulb is dim, we are losing energy, we're losing voltage as well. The bulb is only getting about 4 volts, so somewhere we've lost 8 volts. We've lost 8 volts across the cables. Is there anything we can do about this? Well, yes. What we can do is we step up the voltage. We have a step-up transformer, and we're going to step it up from 12 volts to about 240. Okay, that 240 volts is on the power lines, but then before the bulb gets it, we step it down again. So we step up the voltage, then we step down the voltage after the power lines, and the bulb is nice and bright, 12 volts. Okay, so before putting the electricity on the power supply, on the power lines, we step it up, and then just before it gets to the bulb, we step it down again. And clearly, it is more efficient. We are losing a lot less energy, and you definitely wouldn't touch these cables because you'd get zapped. So if we transmit electricity at high voltages, it is much more efficient. Why? Okay, now study this and try and learn it. Remember another equation for power, P equals I squared R. It's on one of my electricity videos. Now, P equals I squared R. Imagine P here is the power lost in the cables. Now, the power lost in the cables will depend on the resistance of the cables, so that should be as small as possible, and it will depend on the current, and so that should be small, and it will really depend on the current because in this equation it's I squared. Okay, so a difference in the current is going to make a big difference in the power that we lose. So basically, we want to keep the current small. We want the current in these power lines to be small as possible. So how do we have a small current in the power lines? Well, what we do is we step up the voltage. And if you were listening earlier about transformers, if we step up the voltage, then we step down the current. So the current in the power lines is small, and then before it gets to our house, we step down the voltage again, so the current gets bigger. On the national grid, on parts of the national grid, electricity is transmitted at 400,000 volts. Okay, so from the power station, I believe it comes out at about 11,000 volts. It's stepped up to 400,000 volts. Before it gets to us, obviously for safety reasons, it's stepped down to a relatively safe 230 volts. If they didn't do that, then there'd be like lightning bolts jumping out of sockets at you. So it's stepped down to about 230 volts for safety reasons. Here's an interesting little thing to finish off with. One of the reasons we get alternating current, we get AC, is because it can be stepped up. Yeah, you can't step up DC. So one of the reasons we get AC is because it can be stepped up and stepped down, and so it can be transmitted much more efficiently. So who are these two blokes here? You should know the first one when we talked about magnetic fields. And the guy on the right, Americans think that he invented the light bulb, but we know that it was Joseph Swan.